today's lecture we discussed non-ideal solutions, deviations from ideality, azeotropic solutions, colligative properties, relative lowering in vapor pressure and Raoult's law. In today's lecture, we are going to discuss some more examples related to Raoult's law, measurement of relative lowering of vapor pressure and elevation of boiling point. You know that Raoult's law for dilute solutions states that the relative lowering in vapor pressure of a solution in which non-volatile solute has been added is equal to mole fraction of solute. We are discussing some examples related to Raoult's law. Calculate the vapor pressure lowering caused by addition of 50 grams of sucrose to 500 grams of water if the vapor pressure of pure water at 25 degrees Celsius is 23.8 millimeters of mercury. Now, according to Raoult's law, relative lowering of vapor pressure is equal to mole fraction of solute, means P naught B minus Ps upon P naught B is equal to Wa upon Ma divided by Wa upon Ma plus Wb upon Mb. Here Wa upon Ma is equal to 50 upon 342, which is equal to 0.146, and moles of solvent, which is equal to Wb upon Mb, is equal to 500 upon 18, equal to 27.78. Substituting all these values in the Raoult's law equation, we will get P naught B minus Ps equal to 0.146 multiplied by 23.8 divided by 0.146 plus 27.78, which is equal to 0.124 millimeters of mercury. Here's another example related to Raoult's law. The vapor pressure of pure benzene at a certain temperature is 640 millimeters of mercury. A non-volatile solid weighing 2.175 grams is added to 39.0 grams of benzene. The vapor pressure of the solution is 600 millimeters of mercury. What is the molecular mass of the solid substance? Again, using the Raoult's law equation, P naught B minus Ps upon P naught B equal to Na upon Na plus Nb, we will get the solution. Let Ma is the molecular mass of the solid substance. Now, number of moles of solute will be equal to 2.175 upon Ma, and number of moles of solvent will be equal to 39 upon 78 equal to 0.5. It is because molecular mass of benzene is 78. Substituting all these values in Raoult's law equation, you will get Ma, that is molecular mass of solute, to be equal to 65.25. We can also calculate the weight of the solute required to get some desirable decrease in vapor pressure. What mass of non-volatile solute, which is urea, needs to be dissolved in 100 grams of water in order to decrease the vapor pressure of water by 5%? What will be the molality of the solution? Now, we can use the modified form of Raoult's law, which is equal to P naught B minus Ps upon Ps equal to moles of solute upon moles of solvent. Here P naught B is equal to 100 millimeters, then Ps is equal to 75 millimeters. Now, 100 minus 75 divided by 75 will be equal to Wa into 18 upon 100 into 60. As molecular mass of urea is 60 and molecular mass of water is 18, Wa will come out to be 111.1 grams. Molality of the solution will be equal to Wa multiplied by 1000 divided by Ma into Wb. Now, Wa, as you have calculated, is equal to 111.1, hence molality will be equal to 111.1 multiplied by 1000 divided by 60 into 100, which comes out to be 18.52 molar. There is another example to practice more of Raoult's law. A solution containing 30 grams of a non-volatile solute in exactly 90 grams of water has a vapor pressure of 21.85 millimeters of mercury at 25 degrees Celsius. The new vapor pressure becomes 22.15 millimeters of mercury at 25 degrees Celsius. Calculate molecular mass of the solute and vapor pressure of the water at 25 degrees Celsius. Here you have to make two equations with two variables. Let the vapor pressure of water at 25 degrees Celsius is P naught B and molecular mass of the solute is Ma. By using Raoult's law equation, means modified Raoult's law equation, P naught B minus Ps upon Ps is equal to moles of solute upon moles of solvent. You will get first equation P naught B minus 21.85 divided by 21.85 equal to 30 into 18 divided by 90 into Ma. For second solution, we get the equation P naught B minus 22.15 divided by 22.15 equal to 30 into 18 divided by 108 multiplied by Ma. Now dividing the equation 1 by equation 2, we will get P naught B minus 21.85 divided by 21.85 divided by P naught B minus 22.15 divided by 22.15 equal to 108 divided by 90 equal to 6 by 5. You will get P naught B equal to 23.78 millimeters of mercury. Substituting the value of P naught B in equation 1 or in equation 2, you will get Ma is equal to 67.9 grams per mole. We can measure relative lowering of vapor pressure experimentally by two methods, static method and dynamic method. Dynamic method is also called Ostwald and Walker method. First, we are going to discuss static method. In this method, the vapor pressure of the solvent is determined by the usual barometric technique and the difference in the vapor pressure of the solvent and the solution, that is P naught B minus Ps, is determined with the help of a differential manometer. One arm is connected with the solution and the other arm with the solvent. You can have a look on the figure for static method. An oil or any other suitable liquid of low density is used as the manometric liquid. The difference in the vapor pressure can thus be read directly from the difference in the levels of the liquid in the two limbs. There is another method to measure relative lowering in vapor pressure experimentally. It is dynamic method, which is also known as Ostwald and Walker method. Have a look on the figure related to its apparatus. It consists of two sets of bulbs. The first set of 3 bulbs is filled with solution to half of their capacity and second set of another 3 bulbs is filled with the pure solvent. Each set is separately weighed accurately. Both sets are connected to each other and then with the accurately weighed set of guard tubes filled with anhydrous calcium chloride or some other dehydrating agents like P2O5, concentrated H2SO4, etc. The bulbs of solution and pure solvent are kept in a thermostat maintained at a constant temperature. A current of pure dry air is bubbled through. The air gets saturated with the vapors in each set of bulbs. The air takes up an amount of vapors proportional to the vapor pressure of the solution first, and then it takes up more amount of vapors from the solvent which is proportional to the difference in the vapor pressure of the solvent and the vapor pressure of the solution, that is P naught B minus Ps. The two sets of the bulbs are weighed again. The guard tubes are also weighed. Now, loss in mass in the solution bulb is directly proportional to vapor pressure of solution, and loss in mass in the solvent bulb is directly proportional to lowering in the vapor pressure of the solution, that is P naught B minus Ps. Total loss in both sets of the bulbs will be directly proportional to Ps plus P naught B minus Ps, which will be directly proportional to P naught B. total loss in mass of both sets of the bulbs is equal to gain in mass of the guard tubes. Therefore, P naught B minus Ps upon P naught B, that is relative lowering in vapor pressure, will be equal to loss in mass in solvent bulbs divided by total loss in mass in both sets of the bulbs, which is again equal to loss in mass in solvent bulbs divided by gain in mass of guard tubes. Further, we know from Raoult's law that relative lowering in vapor pressure is equal to mole fraction of solute. That is, P naught B minus Ps upon P naught B is equal to Wa upon Ma divided by Wa upon Ma plus Wb upon Mb. This relationship is used for calculation of molecular masses of non-volatile solutes. For very dilute solutions, the relationship can be modified. P naught B minus Ps upon P naught B is equal to loss in mass of solvent bulb upon gain in mass of guard tubes equal to WaMb upon WbMa, that is number of moles of solute upon number of moles of solvent. We can take an example to practice this topic. Air was passed through a solution containing 2 into 10 to the power minus 2 kg of a substance in 0.1 kg of water and then through pure water. The loss in mass of the solution was 2.945 into 10 to the power minus 3 kg and that of pure water was 5.9 into 10 to the power minus 5 kg. Calculate the molar mass of the substance. In Ostwald and Walker method, we have learned that relative lowering in vapor pressure is equal to loss in mass in solvent bulb upon loss in mass in both sets of the bulbs. Therefore, we get P naught B minus Ps upon P naught B is equal to loss in mass in solvent bulbs upon total loss in mass in both sets of bulbs. Now, loss in mass in solvent bulb is equal to 5.9 into 10 to the power minus 5 and loss in mass in solution bulb is given as 2.945 into 10 to the power minus 3. Hence, P naught B minus Ps upon P naught B will be equal to 5.9 into 10 to the power minus 5 upon 5.9 into 10 to the power minus 5 plus 2.945 into 10 to the power minus 3, which is equal to 5.9 into 10 to the power minus 5 upon 3.004 into 10 to the power minus 3. Now, we also know that relative lowering in vapor pressure is equal to moles of solute upon moles of solvent for dilute solutions. Therefore, we get that P naught B minus Ps upon P naught B is equal to 2 into 10 to the power minus 2 into 18 upon Ma into 0.1. Therefore, Ma is equal to 2 into 10 to the power minus 2 into 18 into 3.004 into 10 to the power minus 3 divided by 5.9 into 10 to the power minus 5 into 0.1, which is equal to 183.3 grams per mole. Now, we are going to discuss an example which is related to liquid-liquid binary solution and Raoult's law. This is also related to Dalton's law. In the equimolar solution of benzene with mole fraction equal to 0.5 and that of toluene with its mole fraction equal to 0.5 again, benzene lowers the vapor pressure of toluene and toluene lowers the vapor pressure of benzene. Compare vapor composition versus solution composition. Here, P naught benzene means vapor pressure of pure benzene is equal to 95.1 torr and vapor pressure of pure toluene is equal to 28.4 torr. Now, P benzene, that is partial vapor pressure of benzene, will be equal to mole fraction of benzene into vapor pressure of pure benzene, which is equal to 0.5 into 95.1 torr equal to 47.6 torr. Partial pressure of toluene will be equal to mole fraction of toluene in solution phase multiplied by vapor pressure of pure toluene. This is equal to 0.5 into 28.4, which is equal to 14.2 torr. total pressure will be equal to partial pressure of benzene plus partial pressure of toluene, which is equal to 47.6 plus 14.2, which is again equal to 61.8 torr. Now we have to calculate the mole fractions of benzene and toluene in vapor phase. So, mole fraction of benzene in vapor phase will be equal to partial pressure of benzene upon total pressure, which is equal to 0.5 into 95.1 divided by 61.8 equal to 0.770 torr. Similarly, mole fraction of toluene in vapor phase will be equal to partial pressure of toluene upon total pressure, which is equal to 0.5 into 28.4 divided by 61.8 torr, which is again equal to 0.230 torr. Now, the mole fractions in vapor phase are totally different from the mole fractions in solution phase. Now, we are going to discuss another colligative property named as elevation in boiling point. Elevation in boiling point is studied under the class ebullioscopy. To understand elevation in boiling point, we must know what is boiling point. Boiling point is the temperature at which the vapor pressure of the liquid becomes equal to the vapor pressure of atmosphere. Vapor pressure of the liquid is lowered on adding non-volatile solute to the solvent. Therefore, the difference between the vapor pressure of the solution and atmospheric pressure becomes larger and boiling point increases. Hence, the temperature of the solution when its vapor pressure will be equal to atmospheric pressure will be higher than the temperature of the pure solvent. The boiling point of concentrated solution is always greater than the boiling point of dilute solution. It can also be said that the boiling point of the solvent is elevated by the addition of non-volatile solute. The difference in the boiling point of the solution and the boiling point of the pure solvent is termed as elevation in boiling point. In the phase diagram for pure solvent and solution, you can see that vapor pressure of solution decreases, hence boiling point of the solution increases. This increase in boiling point is known as elevation in boiling point. Now we are going to derive an expression for elevation in boiling point of solution. Here we have taken delta Tb is equal to boiling point of the solution minus boiling point of the solvent. This is equal to elevation in boiling point. This can be better understood by plotting a graph of vapor pressure against temperature for a pure solvent and two solutions of different concentrations. Here is the graph, you can have a look. Here is the line for pure solvent. For the solution 1, we are getting the vapor pressure lower than pure solvent, and if we add some more solute in it, we are getting vapor pressure even lower than the solution 1. As vapor pressure lowers, its boiling points increases. The curves of the solutions always lie below the curve of the pure solvent. The line P0C represents the atmospheric pressure, T0, T1 and T2 represent the boiling points of pure solvent, solution 1 and solution 2 respectively. The vapor pressure of pure solvent, solution 1 and solution 2 at temperature T0 are P0, P1 and P2 respectively. Assuming that the solutions are very dilute, these curves can be taken to be straight lines near the boiling point. Hence, triangle ACE and triangle ABD are similar. Therefore, AC upon AB will be equal to AE upon AD. These are the properties of similar triangles. Hence, T2 minus T0 upon T1 minus T0 will be equal to P naught minus P2 upon P naught minus P1. Now, T2 minus T naught is the increase in boiling point for second solution, and T1 minus T naught is the increase in boiling point for first solution. Hence, it can be taken as delta T2 upon delta T1 means elevation in boiling point for second solution upon elevation in boiling point for the first solution. P naught minus P2 is the decrease in vapor pressure for second solution, and P naught minus P1 is the decrease in vapor pressure for first solution. Hence, P naught minus P2 upon P naught minus P1 can be taken as delta P2 upon delta P1 means decrease in vapor pressure for second solution upon decrease in vapor pressure for first solution. From this equation, we can say that delta TB is directly proportional to delta P, means elevation in boiling point is directly proportional to decrease in vapor pressure. From Raoult's law for dilute solutions, we can say that relative lowering in vapor pressure is equal to number of moles of solute upon number of moles of solvent. That is, P naught B minus Ps upon P naught B is equal to WaMb upon WbMa. Here Ps is the vapor pressure of the solution. It can also be written as P naught B minus Ps equal to WaMb upon Wbma multiplied by P naught B. For the pure solvent P naught B, which is the vapor pressure of pure solvent at its boiling point, and Mb, which is its molecular mass, are constant. Therefore, we have P naught B minus Ps, which is directly proportional to Wa upon Ma Wb, or delta P is directly proportional to delta Tb, which is again directly proportional to Wa upon Ma Wb. Here delta P is decrease in vapor pressure and delta Tb is increase in boiling point. We can have another equation, delta Tb equal to K Wa upon Ma into Wb. Here K is the proportionality constant and is known as elevation constant. If 1 mole of solute has been taken, that is Wa upon Ma is equal to 1 in 1 grams of the solvent, then Wb will be equal to 1. Therefore, delta Tb will be equal to K. Thus, boiling point constant is equal to the elevation in boiling point, which would be theoretically produced when 1 mole of a non-volatile solute is dissolved in 1 gram of the solvent. If we are taking 1 mole of solute again, but in 100 grams of solvent, then delta Tb will be equal to K upon 100. As K upon 100 is again a constant, it can be replaced by K dash. Here K dash is called molecular elevation constant. K dash, that is molecular elevation constant, is defined as the elevation in boiling point produced when 1 mole of the solute is dissolved in 100 grams of the solvent. Therefore, K will be equal to 100 K dash. Putting this value in equation 1, we get delta Tb equal to 100 K dash Wa upon Ma into Wb. This is taken to be equation number 2. If we are dissolving 1 mole of the solute in 1000 grams of the solvent, then Wa upon Ma will be equal to 1 and Wb will be equal to 1000. Then delta Tb will be equal to K upon 1000. As K upon 1000 is again a constant, it can be replaced by another constant Kb. This Kb is called molal elevation constant or ebullioscopic constant. Ebullioscopic constant or molal elevation constant is defined as the elevation in boiling point produced when 1 mole of the solute is dissolved in 1000 grams of the solvent. Hence, we get K is equal to 1000 Kb. Putting this value of Kb in equation 1, we get delta TB is equal to 1000 kb WA upon MA into WB. This is the equation number 3. Or we can say that delta TB is equal to Kb into molality. It is because molality is equal to 1000 into WA upon MA into WB. The elevation in boiling point of a solution of non-electrolyte is proportional to its molality, and equimolar solutions of all the substances in the same solvent will show equal elevation in boiling points. We can take an example to understand elevation in boiling point. On dissolving 10.8 grams of glucose with molecular weight 180 in 240 grams of water, its boiling point increases by 0.13 degrees Celsius. Calculate the molecular elevation constant of water. Now, delta T is equal to 100 K dash multiplied by WA upon WB into MA. K dash is equal to delta T into WB into MA upon 100 into WA. Here, given that delta T is equal to 0.13 degrees Celsius, WB, that is weight of solvent, is equal to 240 grams and molecular mass of solute is 180. WA is equal to 10.8, WA is the mass of solvent. K dash will be equal to 0.13 into 240 into 180 divided by 100 multiplied by 10.8, which is 5.2 Kelvin kg per mole. In this lecture, we discussed some examples related to Raoult's law, measurement of relative lowering of vapor pressure by two techniques, static method and dynamic method. Dynamic method, also known as Ostwald and Walker method. We also derived a relationship for elevation in boiling point. This relationship is delta TB is equal to Kb into molality. In our next lecture, we will focus on some more examples related to elevation in boiling point, some measurement techniques for the measurement of elevation in boiling point and depression in freezing point.